We get a critically damped response when the characteristic equation of the second order homogeneous differential equations has a discriminant delta that is simply equal 0, which means alpha and omega 0 are equal. So we know that the discriminant is simply b squared to alpha squared minus 4 times 1, which is a times b, which is omega 0 here, and that's basically squared, or no, omega 0, well, omega 0 squared here, which is just simply 4 alpha squared minus omega 0 squared. So if they are equal, if alpha is exactly equal to omega 0, that means the discriminant is 0, and we know that S1 is the same as S2, and it's simply just S, and that root is just simply negative alpha. So if I'm plotting those solution for this quadratic equation in the real imaginary complex number, what we get is a couple of poles in here, and these basically are duplicate. Okay, so these are S1 equals S2, and that number is negative alpha, which is a negative number in here. All right, so initially what we said is the complementary solution for such a homogeneous equation should be of the form of k1 e to the power of s1t plus k2 e to the power of s2t, because we assume that they are different s1 and s2. So if you substitute what s1 and s2 are equal to, which is just simply alpha, what you'll end up with is k1 plus e to the negative alpha t plus k2 e to the negative exactly alpha t. That means it's just simply equal to k1 plus k2 e to the negative alpha t, which is just simply, I can rename it as k0 e to the negative alpha t, and that's the complementary solution. Well, this is a solution. However, typically for a second order circuit or a second order differential equation, we will have two initial conditions, and two initial conditions cannot satisfy just one in here. So what we need to, as it turns out to be, that our assumption that this is a good solution is not necessarily the good one. So what we can say instead is that the solution for this complementary solution is the following. It'll be k1 e, well, we're not going to be using s1 and s2 anymore, negative alpha t plus, I'm going to highlight the difference. We're going to do, well, we're going to do k2, okay? And now instead of multiplying directly by e to the negative alpha t, what I'll do is I'll include a t in here. So that's the difference between our original assumption and this assumption. And in this particular case, you can double check that this actually is a valid solution for the homogeneous complementary, for the homogeneous here, differential equation, because you can substitute, you can take the first derivative and the second derivative and substitute them in here, and you'll end up with 0. And I'll leave this as an exercise for you. But for now, this will be the complementary solution for a critically damped response. So what you do is you start with the differential equations, you'll end up with a characteristic equation. The characteristic equation gives you a discriminant that is 0. You know that it's doubled, so what you can do is you can tell me that the solution is of this form. Of course, now we have two unknowns in here, or two constant. We can just use the initial conditions as usual. We can just say, well, when t equals 0, you can tell me that, well, again, x of t should be the particular solution plus the complementary solution. This is just the complementary solution. So what we can do is we can say x of 0 is just simply the particular solution evaluated at 0 plus k1 e to the power 0 plus k2 times 0. So k2 times 0 is just simply that. Okay, and that will be here is the first equation that I am after. And of course I can clean it up because e to the power 0 is just 1. So what we end up with is the following. So that's the first initial condition. Now the second initial condition that we can use is dx of t, for example, evaluated d of t. And when t equals 0, we can just simply say, well, it's the particular, again, if the particular solution happened to be constant, that means the derivative that evaluated at 0 or any other value will be 0. So I'll just focus on the complementary solution because we're talking about DC sources in here. What we'll end up with is k1 times negative alpha e to the negative alpha t plus, I believe this one here also we will have to apply product rule. So product rule tells me that is k2 e to the negative alpha t plus k2, and that will be times t times negative alpha e to the negative alpha t. All right, so we're going to evaluate everything at t equals 0, so that will tell me k1 times negative alpha e to the power 0 is just simply 1 plus k2 e to the negative alpha, which is just 0, plus, well, it will be 0 because there's a t in here. Okay, so what we'll end up with is the following: dx of t evaluated d of t at t equals 0 will be simply negative alpha k1 plus k2, and that's here is the second equation that we're after. We use these two equations, we solve them, and what we end up with is the value of k1 and k2. We substitute them in here, which is here, and we substitute them here, and we'll end up with the solution of this homogeneous differential equation, the complementary solution of the homogeneous differential equation. You add xp of t to it as well.